Have you ever been somewhere where it's really dark at night? Maybe out on a cruise ship or in a field or out camping, and you've seen an amazing night sky. That night sky is what the ancient peoples saw every night without light pollution. And it was common for them to wonder, how do all these stars work and what's our place in the universe? And ever since ancient days, they've developed models to try to understand how the stars and planets moved. They were developed in places like Babylon, ancient China, and Israel, and also in the first mathematically precise way in ancient Greece. And in this unit, we're going to learn all about the motion of the planets. This video will focus on the development of those models over time, so kind of like a history of the solar system. We'll start with the ancient Greeks and move all the way forward to Einstein. Let's learn about this important history. Let's take a look at our lesson objectives for this introduction to Unit 5. Unit 5 is all about gravitation and the solar system. So we'll give you an overview here. First, we'll introduce Ptolemy and ancient astronomy. Ptolemy is like the king of ancient astronomy who came up with an Earth-centered or geocentric view of the solar system. Even though the Earth isn't at the center of the solar system, Ptolemy's model was extremely accurate at predicting the positions of the planets over the course of the year. Then we'll introduce Copernicus and Renaissance astronomy, where we see a shift to a heliocentric model that places the sun at the center. Lastly, we'll introduce Einstein and modern models of gravitation. We'll start with the Greek philosopher Anaximander. In 560 BC, he proposed a model of the solar system with the Earth at the middle. But Ptolemy came along and made that model very accurate. He developed a geocentric model that predicted the position of the planets really well. Here's what the geocentric model looked like. The Earth is at the center, and then there's circles that the planets and the moon and the sun all orbit the Earth on. The Greeks were obsessed with circles. And the thing about circular orbits is they weren't very accurate. So to make his model accurate, Ptolemy had to do something funny. He developed an epicycle. Basically, he put a circle on a circle. That red dot there represents the planet, and the open circle in the center represents Earth. And both of these rings spin at the same time. And by choosing these circles carefully, he developed really accurate models of the solar system. The ancient Greeks developed a geocentric model. And remember that geocentric means that the Earth is the center of the solar system. This model dominated for 1,500 years. So that raises the question, why think the Earth is at the center? Well, the first is that the Earth appeared not to move, so they fixed it at the center and said it doesn't move at all. It appeared not to move because if the Earth is moving, then at different times of years, the stars should appear differently. This couldn't be observed by the ancient Greeks. It turns out with modern instrumentation, we can actually observe this change. The second reason to think that the Earth is at the center is that Venus's brightness is relatively constant. I'm not even going to attempt to explain why this observation is consistent with the geocentric model, but the point is that the Greeks were thinking very carefully about their models and using all the observations they could to develop very accurate predictions. And that's reason 3. Ptolemy's models accurately predicted the position of the planets, so good reasons to think that it's true. And people remained using this model for 1,500 years until Copernicus. In 1540, he shifted to a heliocentric model. Why? He wanted to recover the circular orbits without these weird epicycles. And so he suggested that the sun was at the center, and then all of the planets were moving in nice circles around the sun. So Copernicus developed a heliocentric model, which says the sun is the center of our solar system. This was not accepted initially. So what delayed the acceptance of the heliocentric model? First, and again, the Earth appeared not to move. It still seemed like the Earth was still. Does it feel like you're moving around the sun at 60,000 miles per hour? No. Second of all, it's a radical new idea, and there's hesitancy to accept radical new ideas, especially when there's a lack of evidence. And there wasn't any observations Copernicus could point to that made his model preferable to Ptolemy's. Now, it turns out Copernicus's model was actually less accurate than Ptolemy's, until Johannes Kepler comes along and fixes it. He breaks a significant rule of the Greeks and of Copernicus. He took a nice circle and he stretched it into an ellipse. And his model uses elliptical orbits. Let's take a look at Kepler's laws of planetary motion. These are accurate, and we'll study these in detail. First up, the planets' orbits are elliptical. So the sun's at the center, and the planets move around the sun, not in circular orbits, instead in elliptical orbits. Secondly, the speed of each planet varies, and we'll talk about how it varies in later videos. Third, orbiting objects move faster as they get closer to the center. Orbiting objects move faster as they get closer to the center. What exactly does that mean? Well, let's take a look at this orbital period chart. Notice the Earth has an orbital period of 365 days. That means it goes around once every year. Meanwhile, Neptune takes 165 years to complete an orbit around the sun. This is what Kepler's third law is saying. When you get farther away, it takes longer. Now, along comes Newton in the 1600s. And what he does is he explains the gravitational force that's attracting the planets to the sun. And he formalizes it with a mathematical equation. We'll go through this mathematical equation in detail later, but the point is we can calculate the strength of the gravitational force. And the last modern development we'll cover, in the early 1900s, Einstein said that actually a better model of gravity is something called general relativity. And general relativity, which is quite complicated, predicts that even light will be bent by gravity. The impact of gravity on light was confirmed during an eclipse. The star light that passed by the sun was actually shifted in position by gravity. And so Einstein was right that gravity impacts even light. Let's review all of the characters we've studied in this story. Pause the video and see if you can match each of these descriptions to the correct person from history. All right, let's go through the answers here. Who developed the heliocentric model of the solar system? Well, that would be Copernicus. He's the one who first suggested it. 2, who predicted that even light was impacted by gravity? We just talked about that. That was Einstein. Who suggested that the orbits of the planets are shaped like ellipses? Remember, that was Kepler's addition to the model proposed by Copernicus. 4, developed the most important geocentric model of the solar system. Remember, geocentric is Earth-centered, and that was developed by Ptolemy. Lastly, who developed the first mathematical model for the force of gravity? And that would be Newton. Let's review what we've learned. First, we introduced Ptolemy and ancient astronomy. Ptolemy suggested that the Earth was at the center of the solar system and that the planets moved on rings on rings. Then we introduced Copernicus and the Renaissance astronomy. Here we saw that actually we should place the sun at the center of the solar system and we should stretch these circles into ellipses. Lastly, we introduced Einstein and modern models of gravitation, where we saw that even light is impacted by gravity.
Hey, hey.